Hello, everybody, and welcome to today's special edition of METALCON Live, featuring a recording of the highest attended session at METALCON this past October, Debunking Building Airflow Misconceptions, presented live on site by Samuel Gray of Metallic Products and Bill Beals of Thermal. This session is presented in partnership with the MCA. Is your company an MCA member? If not, pay close attention to the slide on the screen. Membership with the MCAA offers lots of benefits, including a 10% discount to exhibit at METALCON in 2023. The MCA and METALCON are also pleased and proud to present the Future Leaders Program. Be sure to check back to both the MCA and METALCON websites for additional information and upcoming 2023 can't miss programming. Speaking of programming, mark your calendars for Wednesday, January 18th, for our annual State of the Industry event. This panel will feature Paul Deffenbaugh of Modern Trade as a moderator and a secret panel of industry leaders that will be announced in the near future. Don't forget to fill out the post-show survey at the end of this presentation to receive your certificate of completion. And if you run into any technical issues, please send a chat to me, METALCON Live, or submit a question in the Q&A area. Without further ado, let's get started.
Talking about the symbiotic relationship between ventilation, insulation, and the associated energy codes. This is an AIA accredited course. Course number is Tango Alpha Charlie Echo Sierra 022, listed right here. Again, thanks for joining us. I hope you learned a lot out of this. So this course is a 1-hour webinar designed to give attendees an understanding of symbiotic relationship between ventilation, insulation, and metal buildings, with additional insight into the latest energy code requirements that affect metal building envelopes. Best practices are one of the topics. Thermal is a registered provider with the American Institute of Architects Continuing Education Systems, AIA CES. Credits earned upon the completion of this program will be reported to AIA CES for AIA members. Certificates of completion for both AIA members and non-AIA members are available upon request. This program is registered with AIA CES for continuing professional education. As such, it does not include content that may be deemed or construed to be an approval for endorsement by the AIA of any material, construction, or any method or manner of handling, using, distributing, or dealing with any specific material or product. Again, going over the AIA courses, this is the information. In order to get the certificate, to get the credit hours, you must do this. Info, email to receive your certificate, email your full name, info at ThermalCon, reference the course number, which is listed top left. So objectives, I'm going to introduce Vice President of Operations for Metallic Products, Sam Gray.
Testing. Y'all hear me okay? Good morning. Welcome to METALCON 2022, Indianapolis. I want to thank you guys for joining us today. We got a lot of great information we're going to pass along to you. Get that clicker. Special thanks to Bridget with Thermal for helping us out with the logistics for today's presentation. Okay, so some objectives that we're going to get into. We're going to learn the science behind high-growth thermodynamics and how it affects a building's longevity. We're going to determine how to calculate air exchanges and what factors to consider in order to figure out what your building actually needs, so that way customers aren't underbuying or overdoing it for a metal building. Understanding how ventilation helps a metal building's insulation performance. That's been a big topic and a big issue as of late. We're going to grasp the history of commercial energy code landscape, including the major governing councils that mandate today's codes, IECC and ASHRAE. Also, we're going to go into the metal building envelope requirements for IECC 2018 and ASHRAE 90.1 TAC 2016 energy code cycle. We're going to learn about metal building insulation systems that meet the latest commercial energy code requirements and the basics of air leakage, intentional and unintentional air leakage, okay? All right, so one observation that we've had over the past couple years is that ventilation, natural ventilation within the metal building has been perceived as an afterthought. It's actually not even thought about. What we found was the MBMA did a hygrothermal analysis and found that there was an increasing number of insurance claims in regards to metal buildings insulation being compromised or damaged due to condensation, okay? And so, funny enough, it kind of became aware that no one knew how to combat this. And that's where I come in. I had my hand up in the back of the room and said, I know exactly how to fix that. So that's what I want to talk to you guys about today. So that's where the intent of this conversation and diatribe's coming from. Okay, so first thing we're going to talk about is hygrothermal dynamics. And I guess that's how you would pronounce it if you're from Egypt, but we're going to break it down, okay? We're going to go through the definitions here. Hygrothermal is quite simply just relating a combination of moisture and heat, okay? It's a very simple concept. Hygro refers to water, and thermal refers to heat. You can't manage a building's heat without also managing the moisture, the RH factor within the building. For an example, if you increase the amount of insulation in a wall, you may also increase the risk of moisture and mold problems due to dew point temperature within the cavity. That's if you have no airflow to combat the condensation. Two elements of hygrothermal dynamics are properties and analysis. The study includes the vapor absorption isotherms, the water vapor permeability, heat capacity, moisture-dependent thermal conductivity, and effusivity. Now that is a fancy word, but basically it just means the rate at which material can absorb heat, okay? Okay, for analysis, it provides information about the movement of moisture, heat, and airflow through your building's enclosed space, such as through floors, walls, assemblies. It can also provide moisture content within an assembly based on various conditions through simulations of interior and exterior conditions. Okay, so you're not gonna believe me, but if I asked 10 people how a hot air balloon works, 8 people would get it wrong. So I am gonna kind of break this down and get back to the basics, because there are engineers and architects within our industry that do not understand the concept that hot air rises. Believe it or not, it's truth. That is a fact. Or it's completely being negated, it's not being thought about. So yeah, we're gonna go back to 3rd grade here just for a minute. I firmly believe that getting back to the basics when it comes to speccing and designing a building is important. We need to kind of reestablish that. So, hot air rises because it's less dense air, okay? Cooler air, meanwhile, is heavier, and because of this awesome thing we have called gravity, it pulls down on it more strongly, okay? So, obviously, if you want a hot air balloon to rise, hot air rises, right? You shoot hot air up into it, it goes up, and the cool air coming down, if you reduce the temperature, it comes down. Literally, here is a depiction of how a hot air balloon works, okay? Hot air rises. Let's start right there, okay? Now, how does that relate to the building? And the building's kind of whitewashed a little bit. I apologize for that. There's more things to take into consideration with airflow and hot air rising within the metal building. You're gonna have all these other external factors that you need to take into account. And I'm gonna be a little bit redundant. I'm gonna touch on a couple points multiple times, but you can't just decide on how to ventilate a building utilizing intake and exhaust based off of cubic feet. The conversation doesn't stop there. There's all these other factors that come into play. Solar radiation, precipitation, wind velocity, your inlet and exhaust elements are gonna be proprietary to all these situations. Your stack height, cubic feet is a factor, okay? So there's a lot of things, and then also the application that goes on within inside the building is applicable to how you want to ventilate the building and help it breathe. All right, so inside a building, if it's a manufacturing environment, you're gonna want your intake system to be as low as possible. That's where you want the cool air to come from, right? Because it's less dense, it's more dense, it's towards the bottom. The cool air is gonna go in through the bottom, it's gonna be sucked through, and because you have an exhaust element up at the top where the hot air escapes, right? It will pull in the cool air at the bottom of the building, thus getting air circulation and air changes within the building, okay? That'll do two things. It will regulate the temperature within inside the building. It's gonna keep everything going on inside. You're gonna have a better, more comfortable work environment for your employees, and it will combat condensation. That's the enemy of this insulation that we all know and love, okay? We'll get to that. Okay, condensation. In Texas, where I'm from, when you walk outside on a hot day with a cold beer, it starts to sweat. I don't know if that's what happens here, but $20 word for that is condensation, okay? Now let's get back to the basics for that. What is that? A change in the state of water from a gas or vapor form into a liquid form. It generally happens when vapor in warm air encounters a cool surface. So it's when two extremes meet is when this condensation enemy occurs, okay? Condensation does not need a solid surface to take place, as it can occur when a warm pocket of water vapor encounters colder gases. This can happen in your building. The dew point temperature and every temperature below it will turn to moisture, which is your RH. You'll see that come up again, into a liquid. So if your dew point is 45 degrees, any part within the assembly surface or within the insulation will change to a liquid. Same effect will occur for 44 degrees, 43 degrees, so on and so on, okay? Y'all with me so far? I know we're in third grade still, so we'll make it out of there, trust me. All right, I spent $10,000 on this graphic to show you, to depict, we had the hot air balloon, now we got a cloud causing moisture. There you go, that's what you get for 10 grand on graphics these days. But the best illustration is clouds floating overhead. Water droplets combine, they become heavy enough to form raindrops. Now inside your building, that condensation will absorb into your building, into your insulation, especially if you have something that's called positive pressure, where it's actually gonna force it into the insulation. That's one of the, we're gonna talk about that in a second, but that's what happens when you don't have proper building management with airflow. Okay, now, so here's the other misconception. And by the way, if you're here for the presentation for debunking building misconceptions, this is the same presentation. We had to change the title to meet AIA certification, so it's the same presentation. What I'm finding out is that people within our industry think that you either need to ventilate a building or fully insulate it. There's no in between, there's no what I'm here to tell you today is that they are in fact symbiotic with each other. They both help each other. We all understand how insulating a building helps the longevity and the life of the building, right? We can all agree to that. How we keep that insulation premium, how we keep the performance of it and the health and the longevity of it is through air circulation, because the thing that's going to destroy it is condensation, all right? So, in the past, science associated with insulation and ventilation, it hasn't been well understood. I feel like I'm the only one talking about it. So that's why I'm here to educate you guys, and this is for wide dissemination. Don't let this be a secret. We know that the amount of insulation is increased, ventilation also needs to increase. When insulation and ventilation are in balance, the relatively warm, moist air dissipates outside the building through your exhaust element, right? If the balance favors insulation, however, warm, moist air becomes cooler as it nears the roof, and when it can't escape, the air accumulates on a cool surface, gonna be your insulation, allowing mold to form. If contaminated, the spaces provide a food source for other things that you do not want in the building, like harmful bacteria, and it also, like I just said, degrades the life and performance of the insulation. Okay, so how do we combat this problem? It's through temperature regulation. That's how we get rid of the condensation problem. No matter how astonishing a building looks, it's a complete waste if it's uninhabitable. This is especially true when a building's primary purpose is for use by people, a manufacturing or warehouse facility. You don't want things to be damaged or compromised due to excessive condensation. Temperature control ranks among the most important parts of the building's design, but like we said earlier, it seems to be an afterthought or just completely not thought about at all. Okay, so how does temperature regulation affect the building? Improved morale and productivity. People working in uncomfortable, hot and cold environments often behave in unsafe manners as their ability to make decisions and or perform multitask deteriorates. I mean, I had to assemble our booth in heat yesterday, and I can tell you, my brain was getting stupid real quick.
I'll say this, there have been studies on the effectiveness and efficiencies of personnel working inside of buildings where they weren't or were not ventilated properly,
Yes,
Actually, that study was done by Harvard.
thank you, Josh. Yeah, it has direct correlation to safety. Expansion of building materials. This is a big one. This leads to misaligned joints during construction, usually with interiors. Some materials are affected more than others. I see a lot of this with screws backing in and out with expansion and contraction, things like that. If the heat isn't managed and you have those extremes, again, expansion, contraction, it's going to cause panels to loosen up, screws to back out, things like that. Additional worker safety concerns. Heat causes workers to be less careful. We just talked about that. Oftentimes they wear less protective clothing. They'll go without PPE that they need to have for the job, and it causes them to be drowsy and heat and fatigue, which obviously leads to safety concerns as well. And again, hitting on expansion, tensile strength, yield strength, and models of elasticity decrease with increasing temperature. The fatigue properties are also affected by temperature, so that kind of goes into what I just said. Okay, so 6 factors, and it's not limited to just these 6. These are just the 6 main ones that affect the temperature. And this goes into where, when you're talking to the company that's providing you these intake and exhaust elements to provide natural ventilation, these are some factors that are going to be a part of that conversation to figure out exactly what it is that you need for your specific building in your specific area. Latitude, altitude, the distance from the sea, air mass circulation, warm and cold ocean currents, and local aspects. This is going to be very specific to your geographical location, okay? So a building in Maine is going to have different needs, wants, and requirements than a building in Florida, okay? There's different challenges there. So based off of who you're talking to for intake and exhaust, you can talk to them, have the discussion about the size of the building, but also the application and the geographical location so you can get what you need. Okay, so helping your buildings breathe from a design perspective, performing a site analysis kind of goes into what I just previously said. Lay out the building on site, plan with the sun in mind, consider windows and bay doors. And the reason why I put that is that if you have a sound intake and exhaust system with your building, you also have to take into account that if you open up a massive bay door or even a single man door, you're changing that system. You're changing the science and how that's operating, all right? So, for example, if it's cold outside and you got a worker and they close all the louvers down towards the bottom, well, that blocks off the intake. And if you left your exhaust element open because they don't know about it, you're gonna have a negative pressure dynamic where you're gonna be sucking air in from the outside. We'll touch base on that here in a second, but that's what I'm saying when you have to consider your bay doors, man doors, windows, things like that. Build for the geographical region and design for natural ventilation, intake and exhaust, okay? 2 elements there. Okay, so 2 things here, airflow exchanges and CFM. We're gonna talk about that. I'm gonna blow y'all's mind on some real simple math here. So, besides the size of the building and the application, this is where art and science comes into play. This is where a conversation has to take place. And I know ideally this needs to happen at the architect, engineer level, but it can happen past that. So first question is, what level of air quality is needed or desired? Based off of you, the workers, what kind of temperature do you want in there? Do you have an OSHA mandate? Or is there a chemical component? Are you producing corrosive chemicals within the building? Let's say, for example, you want to have the building's air changed out completely 4 times in 1 hour to get the desired effect. So notionally, we're going with 4 ACH, air changes per hour. That's how many times air will completely be refreshed inside the building in 60 minutes, okay? So 60 minutes in an hour, right? 4 air exchanges. How many times is 4 going to 60? 15. So we're talking just about exhaust element right here. You'll take the cubic feet of your building divided by 15 gives you the CFM, cubic feet per minute. That's how much air you need to move per minute in order to achieve your ACH. Everybody with me? Okay. So you can use this CFM number to help determine what's needed for your exhaust element. Now, products are available to you that have different ranges of CFM. This product will move this CFM. And so based off of that, this will help you decide and order what you actually need for your building. Second to that, if you're gonna have an exhaust, you have to have what? An intake source, right? You can't have one without the other, otherwise you're screwed up. Intake, you wanna calculate the free area, which is minus like blades and obstructions, things like that. and you'll get your exhaust CFM. You want that to equal your CFM that your exhaust element has. You want your intake to match your exhaust element. Now, if those are out of balance, if you have more intake than exhaust, you're wasting money. You got a lot of cool air in and you can't get enough hot air out. You're wasting money, okay? You're not optimized. If you have the inverse of that, where you have more exhaust than you do intake, guess what you have then? Negative pressure. And what's gonna occur then is you're gonna be sucking air, hot, bad air, could even be leaves or debris or whatever's on the roof, is gonna suck in through the exhaust element and come down onto your workers and cause an improper workplace environment. It's not gonna do what you've designed the building to do, okay? So they must be balanced between the two of them. So that's the math that you would go through, simple math, to make sure that both elements are equal. Now, obviously the conversation has to take place about what are you actually doing within the building. So both of these go together, art and science, okay? Everybody with me so far on that? We're tracking? Not losing anybody? Okay. So this is a small group, so if we have questions, we'll go ahead and take them in real time. If you got questions, we'll answer them. We're gonna have time for that at the end, but since this is a little intimate situation, we'll take them as they come up. So here's some common field issues. Now, you can do everything I just said. Have the best situation for intake and exhaust. You got your natural ventilation set up, but if you don't use it right, there is a component here where you can have user or operator air and cause a problem within your building. And you're gonna end up calling somebody up and say, hey, my roof's leaking. My exhaust system's not working, my roof's leaking. 9 times out of 10, that's because of something you did, whether it's improper installation or you created the negative pressure dynamic that I spoke to earlier, okay? A condition where air pressure is lower in one place in comparison to another. That's what negative pressure is simply. It can introduce contaminated air and air within a high relative humidity in some climate zones. Anytime a window, we talked about this, bay door is open, it can change the balance between intake and exhaust systems. So if you're shutting down the intake system and you have your exhaust element open, that creates the lower pressure within inside here, so air will be forced in through the top, bringing in weather and everything that you don't want inside your building, okay? Now, the other aspect of that, and I see this quite often, because people don't understand the scientific principles that we just discussed, they install these big-ass fans. We all know that brand, right? So they'll have an exhaust element up top, and because it's hot, and they're ignoring the scientific principle, they'll install these fans, and what does the fan do? It's pulling air from up top and shooting it down. So you're pulling air from your exhaust element, where air is supposed to be leaving the building, and you're just shooting it back down at your employees, basically making a convection oven for your manufacturing space. You see what I'm saying? So, you know, big ass fans, they're great for the patio, but not for the building setup when you have natural ventilation systems. So conflicting air management systems will actually hurt you as well, okay? If you're doing natural ventilation correctly, it's cheap, it's easy, it costs you no power to run it, and you can manipulate it based off of seasons, all right? So obviously if it's cold outside, it's freezing, you can shut down your intake and exhaust, and what does that do? Keeps the warm air inside, keeps your employees comfortable, okay? So down here, like we talked about, negative air pressure, that's the depiction right there. Outside air rushes in to try and balance out the air pressure difference. The other danger is positive air pressure. If you have a positive pressure within your building, that's what we talked about before, where condensation is going to be forced into your building envelope through the insulation, damaging it, okay? And then you're going to have all kinds of problems after that. All right, so any questions before we move on to part 2 of the presentation? Anything at all? We'll cover questions at the end. Okay, so without further ado, this guy needs no introduction, but I'm gonna do it anyway. If you don't know him, you damn well should. This is the man, the myth, the legend, Mr. Bill Bills from Thermal. So give him a round of applause. Thanks for having him here. Here you go, Bill.
Thanks, Sam.
Thank you, sir.
Appreciate it. Okay, so Sam and I met in Cabo San Lucas and at a buffet one night. Never knew the guy, got talking. And here we are less than a year later. Based on what he does and what he knows and what I do and what I know, we decided to put this together as a presentation to see how insulation and insulation systems correlate to ventilation. And there's a guy sitting here right now, one of my customers, that did a huge building in New Hampshire that they had a roof leak for 2 years, and they also had a condensation problem for 2 years. The only problem they had was the mechanical system. It was running backwards, creating a negative pressure, and it was sucking moisture from outside the building in, creating the drip. Where is Rob? Yeah. And the reason it took 2 years is they kept hiring the guy that put the mechanical system in to find his mistake. Don't ever hire the guy that did it to find it. Get somebody else to come in and do the reads. And that solved the problem. So ventilation and positive and negative pressure plays a huge role on how your building's going to perform. So my part is on energy codes, because even though Sam talked a lot about the insulation, the energy codes are what dictate the insulation systems, whether it be fiberglass, insulated metal panel, board, doesn't matter. Envelope is measured in U value. So I'll get started on my part of this, and again, if there's any questions as I go, just raise your hand. I'm going to be here till Friday. So as far as the energy codes go, how are we doing on that mic? Test, test. No, I got nothing. Is yours off? All right, we back? Everybody hear me okay? All right. So as far as the energy codes go, surprisingly, you may learn it has nothing to do with me. I just am the messenger. So the ASHRAE standard, which is nothing more than a minimum energy standard of efficiency. It's the minimum standard. They set the bar, so to speak. IECC is actually a code written in language as a code. So although the IECC relies on a lot of the ASHRAE information, the two are quite different, and there's some differences within the two that allow a designer to choose either the ASHRAE option or IECC. Most people don't know this. So if, say, this state of Indiana, say they were IECC 2018, well, C401.2 is called applications. It gives the designer the option to use the ASHRAE 2016 standard as a compliance path entirely, and it's the designer's choice. You don't have to use IECC. And it's a 3-year lag time between the two. That's why you have IECC 18, 21, and going forward to 24. Then the ASHRAE standard is always 2 years behind the I code, but in a 3-year cycle. So if you're using I-18, the only ASHRAE standard you can use as an alternative is the one 2 years prior, because they kind of base a lot of the math and methodologies on that. Yes, sir. They're 2007. You don't even have an energy code. It's 6 and 4 or whatever you want to do. But here's the problem. It's going to change. Ohio is the same, so to speak, and they're going to I-18 on January 1st. That's why I update these on these blogs. That's going from basically anything you want to what are we supposed to do now. So when you make that leap, it's best to be prepared and understand. And semi-heated space, just so you know, ASHRAE has what's called semi-heated space. IECC does not, so that's why a lot of people will use the ASHRAE method, because of the semi-heated space that's within the ASHRAE standard. So that's kind of how they work, 3-year cycles. And as far as the envelopes go in metal buildings, we haven't really had a lot of changes because we're maxed out as far as U value, which is the thermal performance of an assembly. The roof and walls are pretty much R30 to R41 standing seams, fiberglass. Walls are R30 to R41 double layers. It is what it is. We've kind of maxed out. So most of the code changes now are more on the mechanical and lighting sides, which I know Sam talked about as far as that goes. So our industry relies on thermal performances of assemblies. And insulation companies don't just go do their testing and say, here, ours is great, ours is better, because we use NAMA, National Insulation Association, Manufacturers Association, and the MBMA. So we put these 3 nonprofits basically together to fund testing to submit to ASHRAE our results. So when you see a metal building roof in the ASHRAE or IECC as an R19 plus R11 LS, that's because we did all the testing, we submitted it to ASHRAE, they accepted it and published it, so there's no test data required. Once ASHRAE publishes U values for metal building assemblies, it is what it is. And in ComCheck, if you've ever run a ComCheck, you see the drop down, it automatically defaults to the U values that are done through these different organizations. And I'm members of all of them, and right now we have nothing to test because a 10-inch, 12-inch purlin can only use 14 inches of fiberglass. You can't go beyond that. The payback, I mean, ASHRAE standard sets the minimum of a standard efficiency. If that's the minimum, where can we go? We can't go anywhere from there. So I talk about U value and R value. R value is the rating of a material. The U value is the rating of an assembly. Yes, sir. Okay, yep. So I don't know if I get to that one of these slides. So R value is a rating of a material. U value is the rating of an assembly. So back to the, there's a lot of building manufacturers that have gone out and tested systems that they have proprietary to themselves. And that test must be a ASTM Hotbox 1363, guarded hotbox. And the code has what's called the U-factor alternative. And in ComCheck, if you go to drop-downs, it'll say U-factor other. That's what that's for. So if you have test data to say that your assembly with your specific components meets a U value of 035, 037, 041, then you're allowed to use that under the U-factor alternative that exists in ASHRAE and IECC. But when you run a ComCheck and you're using that assembly, when you use U-factor other option, a screen comes up and says you better have the test data to back this up. And you therefore have to submit the ASTM 1363 hotbox test data backing up your U value that you're inserting. So yes, there's other variations of U value systems by manufacturer. They're all, everybody has something a little different, but the bread and butter is in the ASHRAE standard that most people use. So again, U value is like a metal building roof has a U value of 0.037 or 0.035, so 1 divided by U equals R. So if you want to know what the R value of an assembly is, you take the U value. 1 divided by U equals the whole R value of that assembly. And the opposite is true. 1 divided by R equals U. So if you're using board insulation, for example, and it has an R19 rating, 1 divided by R gives you the U value of that assembly, so to speak. Although there's air films and other ways to add to that, but that's the basic reciprocals of one another, U value and R value. Talked a lot here about the U values and why they're important, because at the end of the day, as a builder and as a building owner, do you want to know the R value I just put in your building, or do you want to know the U value, the thermal performance of that wall or roof? I choose the latter. You want to know what the performance of the entire assembly is, especially the mechanical guys, because they can better design a mechanical system now based on the codes that's going to operate at maximum capacity and no moisture in your cavity. And Sam talked a lot about that positive pressure and that negative pressure. Once moisture, relative humidity is introduced into the envelope, it's moisture, water is a conductor of heat, so your thermal performances go down. So it's very important to maintain a dry cross section to maintain the U value that was all tested with dry fiberglass. So every code, every IECC code has this table. It's apparently the only one a lot of people look at. It's called the R value method. So what is the R value method? So we'll look at group. I know this doesn't show up real good, but if you look at 4 and 5, it says R19 plus R11 LS. That's a liner system, and that is already tested, and we know that has a U value of 0.035. It's just an R value table. So here's the other problem, which will come back to that question. Metal building wall, R13 plus R13 CI. There's a reason that's there, and it's ridiculous. So we only had pinched fiberglass for walls tested and published by ASHRAE. So when the code went beyond what we had, the board insulation people are members of ASHRAE, and everyone wanted their pieces of pie. So they just threw board at fiberglass and said, R13 continuous plus your R13 pinched actually has a U value of 0.52. That's the only reason it's in there. We kind of fell into metal framing, and as you guys know, if you're doing metal studs, you're doing cavity and continuous now. That's normal in that construction, but you can't just use board and fiberglass on a wall and call it the best solution. So what are the options? It goes back to the U-factor alternative. You can use anything you want as long as it is tested and has a U value that is equal to or better than code. So the solution is either use board in its entirety, R19 is an 0.52 if you do the math, or you use fiberglass in its entirety. You don't combine the two. It's one or the other. So that U-factor alternative kind of opens up a lot of other options that most people don't realize. And then ComCheck, you hear me talk about that a lot. That's kind of how we trade everything off and make sure the U values, even though we may be below code on the wall, we're still passing because we added U value to the roof and we withdrew it, kind of like a cookbook method or a trade-off method as opposed to cook. So the very next page in every code book, no one seems to read, is the U value method. The roof needs to be an 0.35. The walls need to be an 0.52. And just in case there's any masonry people here, above grade wall, mass wall, you need to have a U value of point. I'll go back. Try to. Back. Mass wall, above grade, R9.5 continuous, R7.5 continuous. Why is that? Because block wall, mass wall above grade is a hole in the wall. It's not insulated, it's not addressed, we have a problem. And because the codes and the U values have gone to where they are at this code level, if you've got a 2-foot kick wall, a 4-foot kick wall, and you do not address it, you will not pass ComCheck. You cannot get a building to pass ComCheck because the roof, extra in the roof, are usually withdrawn just to get the walls to pass, and when you don't address that block, it will fail every time. So there's foam injection systems and there's other variations of block wall innovation out there that people are using. I'm from Maine, so all up and down the East Coast, the foam injection is basically what most people are using now, and it is an ASTM 1363 tested assembly at 0.52, so their block wall is above code, which allows us to use a little less here and there. So even though the R value method is the easy one to look at and everyone understands, I look at U value, and it's all here. Metal frame walls, 0.064, so if you got metal studs, there's a reason they have that continuous there, because you're not going to get to an 0.64 with a 16-inch metal stud and R whatever you want to put in there. You're not going to get there, thus the continuous. But a lot easier to do a board over a metal stud in a construction sequence from inside to out than it is a metal building. You don't just throw board in a metal building and hope it's going to work out. So heat, air, and ventilation. So I talked a little bit about semi-heated space, and in a lot of the country, like even here further south, when you're building these huge warehouses, a lot of people think, well, I'm going to heat it, so I have to bring it to code. It's like, well, no, not necessarily. So here's the math on semi-heated space. These are the BTUs that are allowed. These are your climate zones. So 15 BTUs per hour per square foot. What does that mean? The floor space times 15 is the maximum allowable output in BTUs to qualify as semi-heated space. If you qualify as semi-heated space, then you can do like they do in Indiana, 6-inch roof, 4-inch walls, most likely, because it's the envelope changes and the requirements change under that. So again, as we move forward, what's changing? Well, they're moving that down. So the semi-heated space in ASHRAE, if you look at 5 now, it's down to 12. So they keep bringing that number down. Is semi-heated going to be an option no longer available? No, but you got to pretty much be in climate zone 2 and 3 to really have a chance of meeting that. And the other problem in, again, Maine, where I'm from, semi-heated space in climate zone 6 was 20. That wasn't enough heat to keep the sprinklers from freezing. So you really didn't have a semi-heated option in climate zone 6, Maine and Alaska. Any questions on that part? And again, IECC does not have anything like semi-heated space. That's why you always have an option to opt out of I code, go to the ASHRAE standard. Air barrier. So this has evolved from IECC 2007, which there was a mention of one. IECC 2012, there was a paragraph on it. IECC 2015, there's a half a page. And now at I-18 and I-21, it's 2 pages, it's mandatory, and you have 3 choices as a designer on the air barrier part. And as far as IECC goes and ASHRAE goes, there's not a lot of change in language. So there's no easier method. So the way it has always been written and the way it is still today is you have a materials choice, you have an assembly choice, and you have a blower door testing choice. The designer makes that choice. What is materials? Materials is just that. Every vapor barrier used in metal buildings, whether it be a liner system or a laminated product like you do with your 6, has been tested and can be an air barrier. Even though it's a vapor barrier, it's also tested and can be an air barrier. So under the materials option, you technically have met the materials option. Now joining and sealing and doing everything properly from then on is on you. You still have to maintain that, and it has to be detailed that way. Assembly is just that. So we, through the MBMA, did some assemblies down in Maryland where we built metal building walls with liner systems, 2 3-inch tabs, seal tabs, and tested it, and they all meet the assembly option. So materials is just that, and assembly is just that. Here's the big one, the blower door testing, which is every Army Corps of Engineers job you will have to do. If a designer chooses the blower door, you cannot go backwards. And if the building fails, the GC owns it till it passes. And even though you had a materials choice, once that's chosen and you fail, you can't say, you know what, I'd rather use, it's too late. It's already done, you cannot go backwards. So if you're ever reading a spec or see a spec that says it will be blower door tested, you look at 3 numbers: the positive pressure requirement, the negative pressure requirement, and the allowable leakage. Because for a while it was quite simple, 75 positive, 75 negative, 0.4 leakage. Well, that's now gone to 80 and 90 positive, 110 negative, and 0.25 leakage. That's a lot more difficult to meet. The Army Corps of Engineers, every time they meet and decide we can do 0.25, they're going to 0.1 next. So that target's moving. So the 0.4 right now, for the most part, is pretty easy to meet, but when you start getting to 0.25 and 0.1, it's not that easy. I mean, you take a corner of a metal building and you put a heat gun in Maine outside, you can see the heat flowing right out the corner, as is the air and the air leakage. Those corners and transitions will fail every time. Any questions on that? All right, so here's a lot of the language. A continuous air barrier, the entire building envelope shall be designed and constructed with continuous air barrier. Exceptions: semi-heated space, we've talked about that, or single-wide concrete masonry in climate zone 2B. It's been in there since day 1. I don't know why, don't care. It doesn't matter here because we're talking about metal buildings. Design shall be noted as follows: all air barrier components of each building envelope assembly shall be clearly identified or otherwise noted on construction documents. It has to be basically detailed on your documents for the permit process. Now, a lot of the permitting process guys just look at your drawings and check them off, but technically that's not correct. It has to be drawn in red, shown on the drawings, everything detailed out. And the reason for that is, once you've done that and you build that, you never have to worry about the blower door anyway, because you're going to pass. Blower door testing is becoming mandatory in certain size buildings. Once we get to I-18 and I-21, ASHRAE 19, there's 40,000 square foot and under, and some, I think, 110 and over, huge retail type spaces are requiring mandatory blower door as part of the code and the project itself. So it's worth keeping an eye on this air barrier part of this. That's what I do, but it's not going to go away. And the rest is just basically doors. Everything has to, obviously, any fenestration, any component of the envelope has to be detailed out and tied into the air barrier that you're using. And it doesn't have to just be one thing. Even though we know the vapor barrier can be the air barrier, It can be any combination of materials from the outer part of the envelope to the inner. It just doesn't have to. So you can go from vapor barrier to flashing tape to an air barrier of another source, and as long as they're all combined. So a materials choice doesn't necessarily have to be that material throughout the entire envelope. Fenestrations all have a new test requirement for air leakage, and I'll tell you right now, there's no pass door in this industry, how do I word this, that will meet it after you install it. The test apparatus that they test it in will pass every time, because guess what? It's a perfect world, and it will. But as soon as you step on the threshold and the kerf becomes cut, the air leakage of that door no longer meets this table. So here's the problem I have with all of these tables. On the prescriptive method, if you're doing just that or you're choosing materials, then technically all of your doors and windows are supposed to meet this criteria. The only exception to that is when you blower door test the building and you pass, this becomes irrelevant. You don't have to provide any data on fenestrations to say what their leakage was, because you already met the leakage rate of the building. It's the only exemption to air tightness on fenestration is blower door. So that's why they're moving more towards blower door. And as a building owner, do you want to know that the guy used materials and we're good, or do you want to know what your building tested at? As an owner, I would want to know what it tested at. And how do I get it as tight as it possibly can, maintain the U value that it should, and dryness through ventilation. It's all part of, like I said, the codes and the ventilation and all of what we do is not the problem. It should be your marketing plan. It's a hurdle at first, because a lot of erectors, assemblers aren't used to all the systems that are on the market. But once they perfect one, and they will, like this guy, most of my pictures back there are from jobs he's done. It's your marketing. The owner goes and looks at a job you've done and says, wow, I want this, and here's my air leakage data. So it's not anything that should be, again, the codes aren't going to change. They're here to stay. And when Indiana goes, it's going to be, well, call me. I'll come out and do some presentations for you. We talked about the U factors come from the ASHRAE tables. Once ASHRAE publishes, again, it's other than U factor alternative, it's good to go. So when we look at fiberglass insulation for metal buildings, if you don't know, a liner system is the one that covers the purlin, and the R11 between, these are all the U values associated with each layer. So your first R value is that one, your second R value is that one, and as far as standing seam roofs go, the code is very specific on that, just so you know. These U values are assuming a roof with a 1.5 inch standoff clip. What's that mean? It means that clip stands that roof 1.5 inches off the top of purlin. The thermal block that goes under there must be a minimum of R3, not 5. R3 minimum 1.5 inch standoff is mandatory for code. So all these U values that you see are based on that. So I know there's taller clips and there's variations by different manufacturers, and if you're using something like that, ask for the test data on that to back up the U value so you have it. Because in some cases, long tab banded, you're required to use an R5 because that's what they tested. Any questions on that part? A screw down roof has a U value of 044 with R30. A screw down roof has a U value of 044 with an R50, 60, 70, and 100. There's only one test, and it doesn't matter what you do. It's still a screw down roof at 044. 90% of the country's roof code is 037 or 035. Enough said. You want a comm check and you got a screw down roof, then we're going to have a serious conversation. Nothing against the screw down. Again, they can still use them. I can still get them to pass in some cases. It's great for semi-heated spaces. It's great for unheated buildings. It's great for dairy farms and a lot of market. But in the world that what we're dealing with, don't ignore the thermal performance of a standing seam, because we have so many tests and so many variations. I can always help you out and save you on the walls. Banded liner systems, been around for going on 20 plus years. At first, when we could do 6-inch roof, 4-inch wall. Well, when I started in 1986, we did 3-inch roof and 2-inch walls with white vinyl, and that was the best we had. And then as time has evolved, now we're doing R40s, R50s, standing seam roofs, and the winner is the owner. Because what they used to, I mean, if you guys remember these old metal buildings, mechanicals were constantly kicking on on a hot day. Guess why? Because we didn't have an energy code. And they were very poorly insulated. And it was just air leakage. Well, now that's starting to balance itself out, and the energy savings are there. It's not just the energy for heating and cooling the building, the lighting. Everything has a reduction in cost that allow the owner to go from $75,000 a month in some cases for electricity to $20,000 a month. So again, you guys design, build these things. We are still, as far as I know, 30 or 48% of low-rise commercial. We're the pie, metal buildings. No one else beats us. So we need to be able to move forward with everything we do. Flange brace detailing, in case you don't know, everybody, all the building manufacturers, when you're using a liner system, just make sure you order your building with either a knife plate, double L, because that flange brace detail, if you just don't address it, then you've got a flange brace that's going to bolt to the side of the purlin. You have to cut a hole through the vapor barrier, and you're going to have to try to tape it and make it look good when you don't have to do that. Just make sure they know what you're using. That's a double L. A lot of them are knife plates, nice, clean, slick, no air leakage, and shouldn't have any issues. It's one of his jobs up in New Hampshire. I believe that's where the guy that has the old cars. I mean, what did he say? The cost to heat that in the winter was like nothing, and that's all it was. And it's just a radiant heated seal. And a guy has an old car. I don't have the cars in there, but he has cars collected that had air tightness, liner system, roof and walls, and it was like 20 minutes of heat, and the whole building was 70-some degrees. It's a pretty good win for that guy. So air leakage and infiltration. Basics, I mean, we all think of air leakage as the heat's in your building and it's finding a way out, it's leaking. Well, it also can come in from the outside. You have wind pressures, positive on the windward side, negative pressure on the leeward side, which is a suction, and it sucks the heat right out of the metal building wall, because let's face it, a metal building wall panel is not sealed, it's just a lap. Air can flow through there. So when you have wind hitting your building in the dead of winter, anywhere in the north, that cold air is going through those ribs and into that assembly that you're trying to maintain heat, thus the heat keeps kicking on. So air tightness is a way to control that. So once you add air tightness to the assembly itself of metal building insulation, when the wind's hitting that building, the last thing, the air leakage, what minimizes the reduction. And then when you have wind going over the top of the building, you have the uplift. We all know the UL 90 uplift rating on a roof. Well, that uplift is basically sucking the air off that roof, and that roof will rumble in some cases. So all the heated mass of insulation you got overnight during the morning before the wind kicked up is being sucked right out of the building. So air leakage and infiltration is can be a huge problem. And then you get in the southern, like down in Florida, down in Texas, Mississippi, all these high humid states. On a windy day, you're forcing warm, moist air into your cavity. So the relative humidity is coming from outside in. And it's very hard to control that once it's in there, because the vapor barriers that we use are the best performing in the industry. So what do? We wait for the sun to come up and bake that wall panel, turn that liquid into a gas, and then you got high humid air wants to go to low humid air, and it will make its way back out the same way it got in. But they cycle in and out. And it's that cycling that is your energy loss throughout that day or that month. So air leakage, and then Sam talked a lot about the ventilation and heat rises, the balloon. It's all part of it. Air leakage, infiltration, negative pressure bad, positive pressure bad. Everything should work just like that. Heat rises. These are all the reasons the air barrier part of the code is being written, is to address this. Any questions so far? All right, stack effect is nothing more than that. Warm air rises, sits at the ceiling. If you don't have fans or ventilation, push it back down. It's just going to sit there. So gonna get you out of here pretty quick anyway. So I think we all agree now, based on that information, the building's envelope is defined as a roof, wall, floor that closes a heated, cooled space. Uncontrolled leakage will result in increased energy usage. Your transitions for air tightness. It's all about, that's where your failures are gonna be. I look at a building like a jacket. You know, it's a typical metal building. There's ways to make them airtight. There's air barriers that we can use that will address that wind, and like I talked about, a lot of variations of it based on, I do all these for the Army Corps of Engineers. They get full drawings. We detail everything out. Your building permit goes through just based on what we do. So there's 3 classes of perm ratings. And class 1 is 0.1 perms. Class 2 is 1 point, which is a gallon would pass through, 1/10 of a gallon would pass through. And then a class 3 is 1 point up to 10 gallons, just to give you an idea what the perms are in numbers. So we, in our industry, are class 1, and most of ours are 0.02. 2/100ths of a gallon will pass through a test area based on the test requirement for vapor barriers. So once you get beyond 10, you're no longer considered a vapor barrier. So a lot of the air barriers, I get asked that a lot. You've got 2 vapor barriers. Well, based on the classification, no, we don't. Most air barriers are anywhere from an 18 to a 25 perm. So it goes beyond the classification of a vapor barrier entirely. So that's the difference. I did a lot of testing on some buildings, and I think the results will not surprise anyone. Transitions. So this is a building that was done in Massachusetts. We did it free and offered it up, tried to make it as airtight as we could. That right there is nothing more than a mass wall. They used a liner panel to cover it up. That's a corner. That's infrared lighting. It was 75, I think 75 on the inside of this building and 20 degrees outside. So the thermography worked great because the cold air was pretty obvious. So all your corners leaked. The building failed. So does anyone see a problem if we actually had to go back and fix all that and it failed? You have to pull all the liner panels back off, do a lot of work to bring that back into compliance. That's why I say, so the blower door test, watch that one. Or do it on your own voluntarily to see where you're at, and then you'll know. The electrician came in, did a great job hanging his light and tore all the insulation away and put his wiring in there. Fail, miserably. Top of the pass door, horrible. That door, not bad. That was just the frame, cold. It's the leakage at the top you can see, but for the most part, the door did its job, for lack of a better term. It wouldn't have failed the building. And here's the difference so diffusion is what happens when high humid air or humid air passes through a material, whether it be a vapor barrier, a piece of drywall, whatever. That's diffusion. So a 4x8 gypsum board with diffusion, interior at 70 degrees, relative humidity at 40, 1/3 of a quart of water would pass through there under the process of diffusion. A 1-inch square hole in that same sheet will put 30 quarts of water into that assembly. So I look at that as a metal building wall. When you guys do these liner systems, that's why I'm showing those knife plate, those details. No holes in your vapor barrier. Again, for 2 reasons. That and your air barrier. If you're going to use it as your air barrier, no holes, minimize any holes, and you don't have to worry about passing the air tightness part. And that's it. Any questions? Any of that? All right, for the AIA, thank you. And Sam,
I'm
for
ready.
the AIA.
Thank you, everybody, for joining us. As a reminder, the AIA credit information is going to be at the end of this presentation. You're going to be receiving that survey. It's not technically a survey. It's just so that way we can get your first and last name to input it into that credentialing information, and you can get your AIA certificate. If you do require a certificate, just make sure you fill that out. If you're not an AIA member, that credited certificate will work for you as well. Again, thank you everyone for joining us today. If you do have any further questions, please feel free to send me an email, and you can reach me at Kalyn, Kalyn, at metalcon.com. And I'll be happy to get any information over to our 2 previous speakers, and hopefully we'll be able to get you an answer in short order. Again, thank you all for joining us today. We appreciate your time and we look forward to seeing you on Wednesday, January 18th. Thank you, everyone, and have a great day. Bye.